Welcome to this lecture. This is the third lecture of week 8. Remember, we have been discussing about weak convergence of random variables and we have seen the special example of weak convergence in the form of central limit theorem. We have also discussed about the weak convergence of the random vector setting, and there we had looked at similar properties as done for the weak convergence of random variables. But now we can therefore ask, is there an extension of the central limit theorem to higher dimensions, meaning for random vectors? Just to recall, in the setting of random variables, we have looked at the central limit theorem of the basic example first, which is the classical central limit theorem or the Lindeberg-Levy central limit theorem, where we considered independent and identically distributed random variables from L2, and there we had talked about something about the centered and scaled versions of the corresponding sequence of partial sums, and also we had expressed it in terms of the corresponding sample means. We have seen the extension of those results in terms of the Lindeberg's condition and Lyapunov's condition, and they also imply the extensions of central limit theorem to this more general setting, where the random variables are still independent, but may not be following the same distribution. So, those are what sufficient conditions like Lindeberg's condition and the Lyapunov's condition give us. So, we have discussed several applications of these, and we have also looked at the types of results involving Slutsky's theorem and their applications. So, in this lecture, as we have already pointed out, we are now interested in the higher dimensional analog of the central limit theorem. But note that we just want to explain the type of results that we can get, and therefore, we are going to be concentrating our attention to only the IID random vector setting and see if the results can be generalized. The idea is that if you can extend it to the random vector setting when the random vectors are IID, then ideally with appropriate changes to the assumptions on the sufficient conditions, you can also extend the central limit theorems, but we will not go into further general sufficient conditions. So, without further delay, let us continue the discussion using the lecture notes. So, we are going to discuss, as I said, about the central limit theorem for random vector setting. Note that the limiting distributions that we are talking about, that turns out to be Gaussian. So, this feature therefore, is also expected when you are going to the higher dimensional setting. So, before we go ahead and talk about the central limit theorem in higher dimensions, let us first try to understand the multivariate Gaussian random vectors or multivariate Gaussian distribution in the higher dimensional setting. What we do is that we first fix our notation that we are always going to work with this arbitrary, but some fixed probability space omega f p. So, let us recall some basic facts about the multivariate Gaussian random vectors. We are going to say that d dimensional random vector, so written this way, that x is made up of these components. So, there should be a transpose here, because we typically write random vectors as column vectors. So, this is the transpose of this row vector here. So, this d dimensional random vector x is said to follow the multivariate Gaussian or normal distribution if you look at all this kind of linear combinations, where you are choosing u like this from R d, then you are looking at all such linear combinations of the component random variables. If this happens to be univariate Gaussian for all such u, then we say that original x is multivariate Gaussian. So, this is one identification of multivariate Gaussian distribution or the multivariate Gaussian random vectors. Now, the law or distribution of such random vectors that we are now considering will be identified by two specific parameters. So, again remember, in dimension 1 when you are talking about Gaussian random variables, all you require is the mean and the variance. So, a similar thing extends in the higher dimensional setting, and there in the higher dimensional setting we have a mean vector, we denote it by mu. So, mu stands for expected value of x, which is essentially the component wise expectation of the component random variable. So, that is the vector that you get, we call it mu, the mean vector, and we also end up with a variance covariance matrix. So, sometimes it is also called only the covariance matrix or also the dispersion matrix. So, the notation is this, that we are going to denote it by capital sigma. So, here the components or the entries of this matrix are of this form, that we look at the jth component random variable and the kth component random variable and look at the covariance between them. So, this matrix is a d by d square matrix or a square matrix of order d. Alright. So, if you are given these two quantities, a mean vector and a variance and covariance matrix, then the distribution of a Gaussian random vector is uniquely identified. In particular, you can also talk about the identification of law or distribution of such random vectors through the joint moment generating function, if you wish, or the characteristic function. So, here as long as you are given the mean vector mu and the variance covariance matrix sigma, then you will have to get this form of the moment generating function and this form of the characteristic function. So, given either one, the underlying distribution of this random vector is uniquely determined. So, just to denote this distribution, what we do? We use this symbol. So, again here we are denoting the d, the dimension here, mu stands for the mean vector and capital sigma stands for the variance covariance matrix. So, we are going to write that x follows the d dimensional or the multivariate Gaussian distribution with mean vector mu and variance covariance matrix sigma. And of course, if these two parameters are given, as we have said, that the corresponding joint moment generating function and the characteristic function are uniquely identified. Now, here you note that there is also these very simple properties under linear transformations and in particular by such linear combinations of the component random variables. So, remember here given any vector u, we are simply therefore looking at the summation of uj capital Xj as j varies from 1 to d. So, this quantity is exactly this u transpose capital X, and therefore, by our understanding this is essentially a one dimensional Gaussian random variable. So, typically we do not write it, but here just for the understanding we are writing the dimension is 1. So, now we are having the distribution given by this, that it is a Gaussian distribution with mean u transpose mu, meaning the idea is here that you are looking at uj mu j, where mu j's denote the component entries of the vector mu. Alright. So, that is what this mean turns out to be, and you can also get the variance of this Gaussian random variable as u transpose sigma u. So, this is a simple property of multivariate Gaussian random variables, that given the mean vector mu and the variance covariance matrix capital sigma, you can explicitly write down the distribution of the linear combination of the component random variables as again Gaussian random variables in terms of these specific parameters with this specific mean and this specific variance. Now, if it so happens that this variance covariance matrix turns out to be invertible, only then the random vector x will be having a joint probability density function. And in fact, we know that what should be the expression of the joint probability density function in this case, that pick up any vector small x in R d, then the value of the probability density function at that point is given by this expression. So, here it is important that the variance covariance matrix is invertible, because first of all I require the inverse here, as well as the fact that the determinant should be non-zero. So, this is where we are crucially using the property that the variance covariance matrix capital sigma is invertible. Note here that if you do not have the fact that this variance covariance matrix is invertible, if it is not invertible, then you still can talk about Gaussian distributions, but it will no more have a joint probability density function. So, in particular what can be shown in those cases is that the under some appropriate transformation you can actually reduce it to a lower dimensional Gaussian random vector. So, essentially that is what it happens, but again in general whatever we are discussing, we are not going to assume the invertibility of this variance covariance matrix sigma. Typically what we know is that variance covariance matrix sigma is only non-negative definite or positive semi-definite. So, in this setting what we are saying is that the Gaussian random vectors that we are going to work with are determined by the mean vector mu and the variance covariance matrix sigma, and we have also pointed out the law of the linear combinations of the component random variables. And we are going to use this information about the law of the component random variables or the linear combination of the component random variables very crucially in our subsequent discussion. So, let us see. So, now we are going to focus on certain convergences. So, there we are going to start off with sequences of such random vectors x n. So, now just to clarify the notation about the components now, what we are going to write is that my nth random vector x n has the components given like this. So, it is a d dimensional random vector with components given by x n 1, x n 2 up to x n d. Now, while we consider such sequences of random vectors, we are also going to have the corresponding sequence of partial sums. So, again we are going to look at this type of expressions for the sequence of partial sums, that for any n greater or equals to 1, we are going to look at the sum of first n random vectors. Now, our interest is in the appropriately centered and scaled versions of this S n. So, we are now going to focus on the corresponding higher dimensional analog of the Lindeberg-Levy central limit theorem or the classical central limit theorem. So, this is the extension that the results that we have already seen earlier in week 7 theorem 9. So, here we first recall that in our previous discussion we have discussed certain properties of weak convergence of random vectors, and there we had pointed out that there was an important technique of reducing the problem of weak convergence of random vectors to one dimensional random variables, and this was by means of appropriate projections along certain directional vectors u. We had called that such a result as a Cramer-Wald device or Cramer-Wald theorem. So, now we are going to use that technique here to establish the central limits theorem version in this higher dimensional setting. Let us see. So, what we are now saying is that we now have a sequence of IID d dimensional random vectors. So, that is what we are given. So, now as soon as we are having such a sequence, we are going to talk about the common mean vector and the common variance covariance matrix. Since they are identical distributions, the mean and the corresponding variance covariance matrix are the same. So, we denote the common mean vector by mu and the common variance covariance matrix by capital sigma. Now, here what we are going to look at is this kind of centering and scaling. So, we call such a quantity as T n. What we are doing is that first of all we are summing up x 1 up to x n, that is my capital S n, we divide by n. So, that is this quantity, and finally, we subtract out the mean vector mu and scale everything by square root n. The result states that as n goes to infinity, this T n converges in distribution to a Gaussian random vector z with distribution like this, that it has mean vector 0 and variance covariance matrix sigma. So, this is the extension of the one dimensional classical central limit theorem or the Lindeberg-Levy central limit theorem that we have seen earlier. Alright. So, let us see the proof. So, what we are saying now is that fix any vector u in R d. then our idea is we have to look at the projection of the T n along the direction of u. So, this is simply the summation of u j with the components of T n. So, that is what we are looking at. So, this is the corresponding projection type thing that we are looking at. Now, if we rewrite T n in terms of the original random vectors, first of all this is in terms of S n first, and then we write it down in terms of the corresponding original sequence x k's. So, here what we have now, note that we have u transpose x k here and we are subtracting out u transpose mu here, and there is a summation that we have to consider, and the scaling now is 1 by square root n. So, the fact essentially is that originally we had square root n outside and 1 by n inside. So, now what we are saying is that we are looking at that kind of a quantity like this, that first we write it in this form S n minus n times mu, and therefore, we are ending up with 1 by square root n then S n minus n mu, and simplified this S n minus n mu as a summation of this form. So, that is what we have done so far. Now, let us focus on these random variables u transpose x k. So, here you note that u transpose x k is nothing but the summation of u j then the components of the random vector x k. So, those are written with this notation j equal to 1 to d. So, that is the linear combination of the component random variables that we are looking at. We are looking at this sequence, but now since u is a fixed vector in R D, we actually are going to end up with IID sequence of random variables. Since the original random vectors x k's were IID, this new sequence of random variables are also IID. Moreover, they will have this common mean given by u transpose mu and the common variance given by u transpose capital sigma u. So, therefore, what we end up having is a sequence of IID random variables for which we know about the mean as well as the variance. So, we are now ready to apply the one dimensional Lindeberg-Levy CLT that we have seen earlier. But before that, we note that if we look at z, which was following our distribution with mean 0 and variance covariance matrix capital sigma, then the u transpose z that we if we look at, then what is happening is that u transpose z will be following the one dimensional Gaussian distributions with mean 0 and variance given by u transpose sigma u. So, there is a correction here that will be made in the lecture notes. So, now if we appeal to the Lindeberg-Levy CLT, in fact, we had modified that version in remark 9 of week 7. So, please go ahead and check this. So, what we are saying now is that under this centered versions, if you look at u transpose T n, that will now converge to u transpose of z in the sense of weak convergence as n goes to infinity. So, this is simply the one dimensional Lindeberg-Levy central limit theorem applied to u transpose T n. But since we have verified this result for all u in R D and u was arbitrary but fixed, therefore, the result will now follow from the Cramer-Wald device that T n converges in distribution or in the sense of weak convergence to the Gaussian random vector z with distribution which is following d dimensional Gaussian distribution with mean vector 0 and variance covariance matrix capital sigma. All right. In the IID setting, that is the proof of the central limit theorem that we have just discussed. All right. So, in this result, note that we have not used any kind of property of capital sigma in terms of invertibility. We do not require this additional assumption of invertibility in this result. So, therefore, as a limiting distribution, we may obtain Gaussian distributions multivariate setting where the variance covariance matrix is not invertible. Finally, we make a small comment that so far we have focused on central limit theorem only for the case of dependent random variables, but extensions of this type of results where the random variables are also considered to be dependent are known. We do not discuss this in this course, but the idea is that originally we start with IID sequence of random variables, then we dropped the assumption on identical distributions, and there we had considered the sufficient conditions by Lindeberg's condition and the Lyapunov's conditions. Now, what we are saying is that we can also further drop the independence assumption on these random variables, and here it is important that we have to therefore focus on certain additional properties of the joint distribution of these random variables. So, that is what we will try to capture the dependent structure involving these random variables. So, there are further extensions of these in terms of something called short range dependence and long range dependencies. So, typically what you would like to look at is whether x1, x2 and xn so on, that sequence that you are considering, whether the first random variable x1 is still dependent on the remaining all random variables or not, and if they are dependent, in what sense they are dependent, can you get some estimates of the covariance structures and so on. That is what is typically done by trying to understand the dependent structure of these random variables when you are trying to consider central limit theorem for dependent random variable setting. So, as mentioned earlier, we are not going to talk about such results in this course. So, in this course we are only considering independent random variables. We stop here. Thank you.